Hi, this is Dalan He from System Research. This session introduces our ELIC paper. It is a practical learned image compression architecture that achieves remarkable performance while maintaining a reasonable running speed. Learned image compression methods use autoencoders transforming images to latent space. By estimating the distribution of the latent variables and encoding them with an entropy coder, the variables can be saved and transferred at low bit rates. Many of the best IORC methods use context models. They refer context to predict the coding features and save bit rates. Existing context models can be divided into three types. The first is an autoregressive model with context variables on the left top. It improves the performance, but introduces an extremely slow serial decoding. To address the decoding speed issue, a checkerboard model is proposed. By using a two-pass parallel decoding, the efficiency is significantly improved. The channel-wise model is another alternative. This model, unlike the other two spatial context models, splits the features into many chunks along the channel dimension. It sees earlier decoded chunks as the context of later ones. These two parallel context models are both powerful. We assume them orthogonal and recommend combining them. So we propose that the context, it better reduces the bit rates by referring both the intra-chunk and inter-chunk context information. Let's have a look at how it decodes. Initially, because we don't have any context to work with, we infer the entropy coding parameters straight from pre-stored hyperprior features and decode half of the first chunk of features from the bit stream. Note that the encoding is similar and we omit it in this video. Then, we see the anchors as context and input them to the spatial context model to infer the other half of the first chunk. The first chunk is now completely decoded. The decoding process so far is applying only the checkerboard context model on the first chunk. After that, we'll decode the second chunk using the first as channel context. We feed the first chunk into the context model and decode the anchors of the second chunk, and then decode the other half with both the first chunk and the anchors as context. As a result, the second chunk is decoded using both spatial and channel-wise context model. And then we decode the next chunk with the obtained tool as channel context. And repeat this loop till the end of decoding all chunks. This chunk-by-chunk decoding costs a lot, as we usually use a k more than 10 to ensure the early performance. Therefore, we further investigate an unevenly grouped channel-wise model to speed up. This is motivated by our observation of unbalanced information distribution among IORC features. We call it the information compaction property of IORC. When using a channel-wise context model, the most important channels with stronger activations are more likely to appear in the earlier decoded chunks. Yet most of the other channels contain much less information, contributes less to the contextual modeling. It inspires us to adjust the grouping granularity. Different from the existing 10-slice grouping scheme, we propose to unevenly group the channels to less chunks. Slicing later decoded chunks coarser saves the calculation volume. Final beginning chunks involve more subsequent features decoding, which also compensates the performance. This promotion can significantly speed up the assay context and achieves comparable performance. Another benefit of adopting this uneven assay context is that we can fast generating thumbnail preview images without downsampling the slowly decoded full-resolution image. Because of the information compaction, we can fast reconstruct the preview images from the partial features with an antenna network called the sum synthesizer. This takes only a few microseconds and further improves the practicality of models with assay context. We implement the assay context into the IORC model to obtain the ELIC model. To further balance performance and inference speed, we simplify the transform networks by replacing GDN layers with more generally used rest blocks. This makes ELIC scalable. Finally, we present the figure to show how ELIC balances the performance and the speed. It achieves a better early performance, where it can real-time decode high-definition images. We believe the proposed method can further improve the IORC study to make it more practical and valuable. This is the end of this session. Thanks for your listening.